How can we solve the Laplace equation in 2D? Let us start with the easiest domain, a rectangle. We can have boundary conditions on all four sides of the rectangle. How do we deal with that? And what procedure can we follow? You will learn all of this in this video. So in this example, I put the u0, y to 0 and ux, 0 to 0 to have only boundary conditions here, y equals b, and here on x equals a. Because if you know how to do this one with only two non-zero boundary conditions, you can do the one with 4 as well. So let's take a look at this case where we have two non-zero boundary conditions. So what do we do then? We split this problem into two. So there we go. So what we do? We have one problem u1 where we have on the top 0 and here are rubbish, and we have a u2 where here we have 0 and on the top we have our rubbish. So we split into two problems where we have 0 on 3 sides and rubbish on 1, and another one where we have 0 on 3 sides and rubbish on 1. Now, if you would have started with rubbish on all 4 sides, you do not split the problem into 2 parts, but into 4 parts, where you have rubbish on one side and 0 on all 3 other sides. So that is the idea. So why does this work? Well, this works because we are living here in a linear world. That's really nice. Because what we have, our u is u1 plus u2. That means that the Laplacian of u equals the Laplacian of u1 plus u2 equals Laplace u1 plus Laplace u2. But they both satisfy the Laplace equation inside our domain. So that equals 0 plus 0 equals 0. So with this u1 and u2, I solve the Laplace equation. Moreover, we satisfy the boundary conditions. If we look, for example, at x equals a, the u at a, y equals u1 plus u2 at a, y. Now this u2 equals 0 and the u1 equals f, so this u at a, y will satisfy f of y, similarly at all the other sides. So our u satisfies the Laplace equation, our u satisfies the correct boundary conditions, so if we find u1 and u2, we can find our u and we are done. So what's the procedure? How do we find our u1 of x and y, for example? Well, now we can use separation of variables. We can look for modes u1, n equals x of x times y of y. Then, because we have zeros on the boundary for y, we can have a boundary value problem for y of y. Find our y of y in terms of some separation parameter. This will yield a differential equation for x of x. Solve the differential equation for x of x in terms of some constants. Then we can expand our u1 of x and y in terms of the u1, n's of x and y with Fourier coefficients. And then finally we use the final boundary condition to determine the Fourier coefficients of our u1 of x and y. Then we have u1 of x and y, and we are halfway. We do the same procedure for u2 of x and y, and then we have our total solution. And as you see, this whole procedure is very, very similar to what we did in the heat equation and in the wave equation. So in the next video, we'll go through all of this in an explicit example.